I want to start this video with a reminder that if we want to find the inverse of a matrix A, we concatenate the matrix A with the identity matrix, and that results in the matrix A inverse showing up in the position. I should write this like this, showing up in the right-hand sort of side of this concatenated augmented matrix. So let's do that. I'm going to use, I think I'll do this with a 3 by 3 matrix. Here's my identity matrix: 1, 0, 0, 0, 1, 0, 0, 0, 1. And the matrix I'm going to use for A, so I don't want this, I want just a dividing line. What I'm going to do with matrix A, or the matrix I'm going to use for matrix A, is also the identity matrix. And the point then is to take matrix A and push through elementary row operations onto matrix A until it becomes the identity matrix, and the result will be the right-hand side displays matrix A inverse. Now, clearly I don't need to do that here because this side is already the identity matrix, and so what shows on the right-hand side here is in fact A inverse. In other words, if I multiply the identity matrix by itself, because these are both that same matrix, then I'll end up with this matrix. Then I'll end up with the identity matrix, right? A times A inverse is the identity matrix. So the point, I know that seems trivial, but the point here, at least at this point, at this stage, is to demonstrate that the identity matrix has an inverse. The identity matrix is what we call invertible. Now I'd like to do the same thing, but this time my matrix A is going to be an elementary matrix. So there's my template, as it were. I'm going to put matrix A in here, and I'm concatenating it with the identity matrix. And the result, once I do push through those elementary row operations, will be, actually I'm going to call this one B. B concatenated with I is B inverse. If I can't do this concatenation, if I can't do the row operations, or if I end up with a row of all zeros, then we say that B does not have an inverse. But what we're trying to show here is that an elementary matrix does have an inverse. So I'm going to start with an elementary matrix. Let's see what happens if I take the identity matrix and go, let's do 3 times row 1 plus row 3, and I'll put that in row 3. So if I were starting with the identity matrix, and I multiplied everything in row 3, everything in row 1 by 3, I get a 3, 0, 0 here. And then I'm going to add 3 and 0 and 0 to 0, 0, and 1 respectively, which gives me, I'm going to call this, I'll call it E3 because it's my third property. I don't care about the numbers of the properties, remember, I just happen to be using that to identify it. I have 1, 0, 0, 0, 1, 0, and 3 plus 0, 0 plus 0, and 0 plus 1. So this is an elementary matrix, the result having come about by multiplying 3 times row 1 and adding it to row 3, and then replacing row 3 with the result. So that's going to be my A. That's going to be or my B rather, that's going to be the matrix I use here. 3, 0, 1. And what I want to show is that B also has an inverse. So I'm going to go ahead and push through those elementary row operations. As you can see, I don't need to do anything with rows 1 or 2 because they are already, on this side here, they're already the rows appropriate for a 3 by 3 identity matrix. The only thing I'm going to need to change is in row 3. And what I'm going to need to do is somehow make this a 1 and this is 0. No, sorry, make this a 1 and this is 0. So this is already a 1, which is good. and everything above it is a 1. It looks like the way to turn this into a 1 would be to multiply row 1 by -3 and add it to row 3. So let me write down what I'm going to do. I'm going to take row 1, I'm going to multiply it by -3, I'm going to add it to row 3, and I'm going to replace row 3. Okay, so I get -1 times -3 plus 3 is 0. -3 times 0 plus 0, and -3 times 0 plus 1. So I've been able to perform those elementary row operations, but remember that what we're really trying to do here is find a sort of new right-hand side. I've kind of mislabeled this here. Let me clean that up a little bit. This is ultimately really going to be I concatenated with B inverse. Here's going to be my B inverse. All right, so I did the row operations on this left-hand side here, but I didn't do it on the right-hand side. I need to continue doing what I did. I didn't need to do any row operations on the first or second rows. But what I did with row 3 was I took 3 times row 1, -3 times row 1, and I added it to row 3. So I need to do that over here as well. -3 times 1 is -3 plus 0. -3 times 0 plus 0, and -3 times 0 plus 1. So now I have, not here, but here, I have the inverse of B. This is the identity matrix. I didn't run out of rows. I didn't end up with all 0 rows. So B has an inverse, and it's here. This is the matrix B inverse. My point in doing this sort of exercise for you, if you will, is to show you that not only does B have an inverse, I found it here, but that it sort of demonstrates that if this is an elementary matrix, right, then this number right here could be any real number. This is happens to be 3, and I can undo that 3. I can turn that into a 0 by multiplying another row by -3 and adding it to that. Well, if I do that there, then I can do it here as well. So what I've done is I've performed elementary row operations not only on B, but also on the identity matrix to turn the thing over on its head, as it were. Notice that the 3, not just by coincidence, is the opposite of the number that we had in B that was kind of in the wrong place. This is the one we wanted to be a 0. B inverse is the opposite of that 3. That only happens with property 3, or elementary row operation 3, where you take a multiple of one row and add it to another row, but it does happen consistently. So that's kind of a nice thing. The other 2 elementary row operations have similar phenomena, I guess I'll call them. I'm not going to outline them in detail the way I did this one here, because I don't think we really need to, but I will say this. All 3 elementary matrices are invertible. We've just shown, I haven't proved anything here. I've shown for a very specific case, a very specific elementary matrix. But I've sort of demonstrated that elementary matrix 3, E3, has an inverse. The same is true for E1 and E2. In other words, the matrix 1, 0, 0, 0, 0, 1, 0, 1, 0, in which I have reversed the orders from the identity matrix. I've reversed the order of the second and third rows. This has an inverse. This matrix has an inverse, as does 1, 0, 0, 0, 3, 0, 0, 0, 1. This is a matrix that's been scaled. Row 2 has been scaled by 3. This matrix also has an inverse. Let's go back to this one and say that E3's inverse is equal to how do I want to do this? Is equal to E3, but the entry that is not 0 in E3 becomes the opposite in E3 inverse. And what I mean by that is just what we noticed here, which was that for E3, the first two rows, and remember this could be this new row 3, this could have been multiply row 2 by 5 and add it to row 1 and replace row 1. So whichever row has been modified here, notice that there's still a 0 and a 1 in the positions that you would expect in an identity matrix, and this entry has a so-called wrong number in it. That should be a 0. For that entry, wherever it happens to be in the matrix, for that entry, the inverse of this matrix is identical to this matrix, except that this number will be its opposite. And that's what we found here, right? This was the inverse of that matrix. The first two rows are the same. In the third row, the last two entries are the same. This so-called wrong number here, the so-called wrong number in E3, eventually became -3, the opposite of 3 in the inverse of that. For elementary matrix 2, we're going to find that, let's call this E2. E2's inverse is just, and I'll just give an example, I think, in this case, rather than writing it out the way I've done here. It's a bit wordy, and I'm running out of room. The inverse of this matrix is going to be this. The first and third rows are the same. It's the second row that's been modified here. So it's the second row that's going to be modified in the inverse. And the result is that the normal entries, the entries that should have been zeros, are still zeros, but the one that should have been a 1, remember we scaled this by multiplying everything by 3, we're just going to scale everything by 1/3. Essentially, it undoes, it inverts the operation that we did to the matrix. And lastly, we call this one E1. That's the elementary row operation of picking two rows and reversing their order. And the inverse of E1 is just E1. They're identical. So knowing what those inverses are is quite useful, but it's really just as important to know that those inverses exist in the first place.